Good evening. Hope everybody enjoyed the music. Yeah, excellent. I'd like to hear that. Wonderful. Welcome to the third lecture in our spring series. I hope many of you went to the first two. I thought they were pretty good. People agree for the most part? I got lots of emails, so I know a lot of people really enjoyed them. Our first two lectures featured senior members of the Carnegie staff. Our last two lectures this year are featuring our younger astronomers, which is something that we very much treasure at Carnegie. We have, in my opinion, the best program for postdoctoral fellows in all of astronomy and astrophysics. These are individuals who just finished their PhD and then they come to Carnegie for additional doing work for a few years, develop their research reputations before moving on to be faculty members. And tonight's speaker, Kevin Schlaufman, is a Carnegie-Princeton Fellow. And that sounds terrible. What terrible institutions you have to be involved with, like Carnegie and Princeton. So it's a really great fellowship. It really is, in my opinion, the best fellowship in all of astronomy because it's a 5-year position where you do 3 years at Carnegie and 2 years at Princeton. Not too shabby. The problem is that our Carnegie-Princeton Fellows, we started this fellowship about 10 years ago, and none of them ever make it to year 5 because they always end up getting snatched for a faculty job within 2 to 3 years. Which is a sign of the success and the level of these applicants. And in fact, Kevin falls in the same category. Unfortunately, he just arrived at Carnegie in September, and he's leaving in December to start a faculty job at Johns Hopkins, so you can't cry for him too much. But it just shows you the quality of the young astronomers we attract at Carnegie. So Kevin comes from Pennsylvania. He did his undergraduate work at Penn State before going to UC Santa Cruz for his PhD. He then was a postdoc at MIT for a bit before coming to Carnegie. And Kevin works on really the hottest field in astronomy. We could not have enough talks on this topic. And so I really hope you'll take advantage of having him here. He's really an expert on many of the techniques about exoplanets. And so I look forward to hearing the questions at the end of his lecture. But let's start by welcoming Kevin to the stage.
Great. Well, thank you very much, John, for that introduction. Thank you all for coming here tonight. I'm honored to be here to tell you about what John said might be the hottest subfield of astronomy right now. And so the field of exoplanets, and exoplanets is the study of planets around stars like the sun, but outside of our own solar system, is very young. It's only been 20 years since the discovery of the first exoplanetary system that fits this definition, and it's a very exciting time to be studying this type of object in the universe. As I said, it's only been 20 years since we discovered the first object of this type, but we now have nearly 3,000 objects like this. Here I plotted year on the x-axis and the cumulative number of exoplanets known as of that date on the y-axis. And it starts from one example right here in 1995, and it scales all the way up to more than 2,000 objects as of this date. So many of these objects are completely unlike the planets in our own solar system. We know of very big planets. We know of very small planets. We know of planets that are much, much further away from their host star than the Earth is from the sun. We know of planets that are 100 times closer than the Earth is to the sun. We know of planets that potentially could have liquid water on their surfaces. At the same time, we also know of planets which are thousands of degrees on their surface that are probably oceans of molten lava. So our universe has produced an enormous diversity of exoplanetary systems which we can observe right now in our own galaxy. And the challenge for me and other astronomers is to both find these objects, but then after we found them, use them to understand how planetary systems like our own might have formed, and also how these systems which we perceive to be more exotic, but that might actually represent the typical type of planet formation in our own galaxy, how does that process occur? But before we can get to that part, we first have to think a little bit more about our own solar system. So this diagram has the Sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, the 8 planets in our own solar system. Now, some of the more senior members of our audience might remember that for a long time, Pluto was considered to be a planet in our own solar system. It turned out that an astronomer based here in Pasadena at Caltech discovered another object in our solar system, even further away than Pluto, that in many ways was comparable to what Pluto was. And everyone understood that we didn't want to call this new object a planet. And so the most logical, consistent thing we could do would be to demote Pluto to this minor planet category and be left behind with these 8 things which everyone agrees probably formed more or less through the same physical processes, and things like Pluto and the other dwarf planets formed through slightly different processes. So Mercury is 4 times closer to the Sun than the Earth, and it's about 20 times smaller in mass than the Earth is. Venus is almost like an Earth twin. It's only 30% closer to the Sun than the Earth is, and it's only 20% smaller. But in every other way, Venus is a very different planet than Earth is. And so one challenge to exoplanetary astronomers, and indeed planetary scientists even in our own solar system, is how you can have 2 planets, more or less the same size, pretty close to being at the right distance away from their star that you might expect there to be liquid water on the surface, and yet somehow they turn out to be very different systems. The planet Mars is only 60% further away from the Sun than the Earth is, and it's about 10 times smaller. Mars formally is in, or very close to, this range of parameter space where one might expect there to be water on the surface of the planet, but Mars no longer has water on the surface. We have some evidence that it might have had it in the past, but at this point in time, Mars is a very dry planet. Now, those 4 planets in the inner solar system are all rocky and relatively small. Once you go out a little bit further into the solar system, you start to see gas giants. These are planets that are 10 or even 100 times more massive than the Earth. Jupiter is about 5 times further away from the Sun than the Earth is, and it is about 300 times more massive than the Earth. It's about 10 times bigger in radius. Uranus is about 10 times further away from the Sun than the Earth is, and it's about 100 times as massive as the Earth. The planets next are Uranus and Neptune. They're a little bit smaller than Jupiter and Saturn. Uranus is 20 times further away from the Sun than the Earth is, and it's only about 15 times more massive than the Earth. Neptune is comparable to Uranus. It's 30 times further away from the Sun than the Earth is, and about 20 times as massive as the Earth. This is what we expected to find when we went out into the galaxy to find other planetary systems. We expected to find small, rocky planets close to the host star, big, gaseous planets at intermediate distances, and small, icy planets at the greatest distances. And as I'll show, what we found is not at all what we expected. Now, this diagram right here is not to scale in terms of the separations between these systems. It's just to scale into their sizes. And so to understand exactly how much space we're dealing with in space, I've made this analogy. So this is City Hall in downtown Los Angeles. According to Wikipedia, it's 454 feet tall. Imagine now that the Sun is scaled down to this size. We put the Sun where City Hall is in downtown LA. Imagine that it's 454 feet in diameter. Then you would have to go 3.6 miles from that point to get to Mercury. And in this case, Mercury would be about the size of Kobe Bryant. Moving on to the next planet in our solar system is Venus. So Venus would be 6.7 miles from downtown Los Angeles. So now we're getting very close to Pasadena, maybe in South Pasadena by that point. And Venus would be about the size of a car. Earth would be actually very close to where we're sitting right now, very close to the Huntington Library. Earth was about the same size as Venus. It would probably be about the same size as a car. Moving on to Mars, that would be 14.2 miles from downtown Los Angeles. So that would get you all the way out to Santa Monica. It would be nice if you could get to Santa Monica in the same 15 minutes it takes a photon to get from the sun to Mars, but that would be asking for a miracle. Moving on to the next largest planet is Jupiter, 48.4 miles from downtown Los Angeles out to San Bernardino, or Riverside. Saturn would be about twice as far again, all the way out this time to Santa Barbara. Uranus, the next planet out in our own solar system, is basically in the middle of nowhere, going up the coast or going inland. There really isn't any landmarks near where you would expect to find the orbit of Uranus, although there is when we get to Neptune. Does anyone want to venture a guess as to what city the orbit of Neptune will be close to? So, Las Vegas? Phoenix? San Francisco. Okay. A couple of guesses. I think San Francisco was probably the closest because it's almost to San Jose. So I think San Jose and San Francisco and, I don't know, I think San Francisco is still probably a better guess than Las Vegas. Anyways, the point is that we're talking about, even in our own solar system, a very large range in distance. Now, I've talked about the distance from the sun to the most distant planet in our own solar system. How far away do you think it would be to the next closest star on this same scale? The moon? Anyone want to guess a multiple of the distance to the moon? 42? Okay, so the nice thing is that we have bracketed the answer. It turns out that if we were to go to the next nearest star to the sun on the same scale, it would be 4 times the distance to the moon. So this is the scale of the problem which we're dealing with. And this is just our own planetary system. Now, our own planetary system, at least out to Saturn, has been known since antiquity. All of the ancient astronomers knew about Mercury, Venus, Mars, Jupiter, and Saturn. But even at 400 BCE, a Greek philosopher named Democritus was already speculating that there were other worlds in our universe. In fact, Democritus is sometimes thought to be the father of modern science because he was part of the first Greek school called rationalism, which required a physical or natural explanation for everything without recourse to what an object wants. And in addition to that, Democritus was also the first person to speculate that the material, the matter, everything that we can see and touch in our universe is actually made up of small discrete particles, which he called atoms. And so even though he had no way of actually testing or verifying these speculations, he actually was on the right track in many ways. Unfortunately, the philosophy and the ideas of Democritus lost out to the philosophy and ideas of Aristotle and Plato, and his ideas were, for the most part, largely ignored for the next 2,000 years. However, eventually there was another individual who had this very creative and perhaps ingenious idea and thought that not only are there other worlds in the universe, the Greek Democritus probably was thinking more along the lines of a multiverse like cosmologists think of multiple universes, but Giordano Bruno, who was an Italian monk and priest in the 16th century, he actually specifically thought that the stars in the sky were for the most part stars just like the sun, and in particular that those stars were also orbited by other Earths. In fact, he wrote, "These other worlds have no less virtue nor a nature different to that of our Earth, and, like Earth, contain animals and inhabitants." Again, he had no way of actually testing this speculation, but he was also on the right track, at least in terms of science. Unfortunately, because the Catholic Church was very powerful at the time, he ran across the Inquisition, and unfortunately, he was burned at the stake as a heretic in the year 1600. So this is basically an unfortunate example of someone who was ahead of his time in terms of his ideas. But this thought that we are not alone in the universe, has been something which humanity has been grappling with basically since the dawn of rational thought. So now we jump ahead quite a bit to the middle and end of the 19th century. And now astronomy at this point has changed from something which was more philosophical to something which was an actual physics-based science. And so this, which I'm showing right here in 1855 and later in 1896, was the first claim of a physical detection of another planet around another star in our galaxy. And in particular, it had to do with observations of this star called 70 Ophiuchi. This observation was first conducted by a man named Captain W.S. Jacob in 1855, and then further work was performed by a man named Thomas Jefferson Jackson C., which is quite the name, kind of like Benjamin Franklin Pierce. Again, some of the older people in the audience might remember that one. And this was an observation of a binary star system. So in a binary star system, the two stars orbit their common center of mass, but you can simplify things by imagining that the more massive object is at rest and is orbited by the secondary object. So these two astronomers observed this particular binary star system as a function of time. They plotted on the sky where the secondary star was as a function of date. And based on these data, they said that, look, this model is not working out. There has to be some other body in this system to actually produce what we're observing. And they asserted that the best explanation was a planet approximately the same mass as Jupiter at a distance comparable to the orbital distance of this secondary star. Unfortunately, it turned out that this observation didn't hold up to scrutiny. If you look at this system in more detail and use physics to actually say, how will gravity cause this system to evolve? The claimed object which they thought they saw would be physically implausible. And their observation was probably because of the observational uncertainties caused by the fact that the Earth's atmosphere is not still. It's very difficult to actually localize a point on the sky very precisely at the type of observatories that these astronomers were working with at the time. So this is actually another recurring theme, at least in the early history of exoplanets, that exoplanets was not the field you wanted to be working in. And the reason you didn't want to be working in it is because people would regularly claim the detection of a planet outside of our own solar system. It would attract a lot of excitement. And then as people looked into it more and more and more, it turned out that what had been seen was not best explained by an exoplanet. It was either some sort of observational uncertainty or some other reason for that observation. And so it was actually very much looked down upon as a subfield of astronomy for basically the next 100 years. All wasn't lost, though, because in 1952, Otto Struve, who at the time was an astronomy professor at UC Berkeley, suggested that there might be a way to make progress using 1950s technology. So Otto Struve was an astronomer who studied these binary star systems, and from the beginning of the 20th century to approximately 1950, binary stars had been one of the hottest fields in astronomy. So binary star systems are basically the one type of astronomical object that you can actually measure a physical property. In most other types of astronomy, we have to estimate something based either on a model or some secondary observations. But in binary stars, you can actually measure how massive a star is and what radius it has. And so he was very familiar with what was the forefront of technology in that subfield. And he said that, look, we now have the technology, at least in favorable circumstances, to find a planet orbiting a star like the sun with a mass comparable to Jupiter that is very, very close to the star, 10, 20, even 50 times closer to that star than the Earth is to the sun. He said that, look, even using 1950s technology, we should be able to find such things if they exist. And not only that, he said that if those things exist, then sometimes the geometry should be just right. That if the star is here and the planet is going around it in its orbit, sometimes things will line up just so that the planet in its orbit passes between the line of sight between the Earth and that star, and that planet would cause the light from that star to fade momentarily as it passed across the disk of the star. And once that planet moved away, the star would come back up to its normal brightness. And if you stared at the star for weeks at a time, you would see this signal repeat. at a very, very regular period, and that would be another smoking gun of the existence of planets. And he basically said that, look, given the tools which we have now in 1952, if such Jupiter-mass planets existed very close to stars like the Sun, we could find them. So these are the techniques which I described in words and now I'll visualize. The first uses the fact that, again, like I said, if you have a two-body system in space, the two bodies don't, the small body doesn't orbit the big body, they orbit their common center of mass. And so if you have a planet orbiting a star, the star is executing a very, very small orbit around the common center of mass. And in particular, the speed with which that star goes around in that circle is proportional to both the ratio of the mass of the star and the mass of the planet. And we can measure this velocity out of the plane of the sky using what's called the Doppler technique. So I'm sure all of you are familiar with the fact that if you're standing on the side of the road and a police car or a fire truck or something goes by you, when the truck is getting close to you, you hear the sound moving to higher and higher pitches. Then once the truck passes you by and starts to go further and further away from you, it moves to lower and lower and lower pitches again. So the exact same physics that happens in that situation is what we can use to find exoplanets using this Doppler technique. So what you do is you take the light that's coming from the star, you spread it out into its constituent wavelengths, and then once you've done that, you can find narrow, dark lines in the spectrum of the star. And those lines correspond to specific transitions in the electron clouds of particular atoms. And we know, based on observations in laboratories in the Earth, very precisely at what wavelengths those transitions should occur. And so you can go out to a star, you can take one of these spectra, you can pick out the lines of interest, and you can measure what wavelength that they appear to be at in this spectrum. And the difference in wavelength between what your laboratory measurement says it should be and what you observe it to be tells you how fast that star is either moving towards you or how fast it's moving away from you. And so if you take many, many, many spectra over the course of the period of the system, you can actually see the star move towards you, you can see it reach its maximum velocity, and then you can see it start to recede. And based upon the period of this signal, and the amplitude of the signal, and some guess about how massive the star might be, you can estimate the minimum mass of the planet necessary to produce that signal. It's only the minimum mass because we don't know the inclination of the orbit. The signal is maximal when the orbit is perfectly aligned, and it's at a minimum if we're looking at the system pole-on. If you're looking at it pole-on, you don't see the signal at all. And so because we can't measure this inclination, all you can see is the minimum mass using this Doppler technique. But the other technique, which Struve suggested might be useful, can help with that regard. So this is the transit technique, which I talked about before, where in this case, imagine that you are looking at a spotlight and a bat is chasing a mosquito. If the spotlight is about 1 meter in diameter, then the dimming of that spotlight when the bat passes in front of it is comparable to the dimming of the starlight of a star when a Jupiter-sized planet passes in front of it. And the dimming of that spotlight due to the mosquito is about the same dip as you would expect when an Earth-sized planet passes in front of a star like the Sun. And using this Doppler technique, you also get, in this case, you can actually say, because I'm seeing this transit at all, I have to know, I know that what the inclination of this system is. I know that it's edge on. And not only that, in this case, with the Doppler technique, you could measure the minimum mass of the planetary system. With this technique, you can measure the radius, because the amount of light it blocks out is proportional to its radius. And so if you have both a Doppler measurement and a transit measurement, you can measure the mass of the planet, the radius of the planet, and with those two numbers, you can get the density. And if you have those things, then you can start to guess, what is this planet actually made of? So this is something which the ancient astronomers would have thought to be impossible. There's no way you would be able to tell what this distant object that you can't even see the light from is made of. But using these indirect techniques, you actually can tell or at least guess, what these very distant objects might be like. So unfortunately, no one followed up on Otto Struve's suggestions, and people continued doing the same things they had been doing before, and exoplanets continued to be a field that you went into at your own peril. There were more suggestions that a planet orbited what's called Barnard's star. So Barnard's star is actually the second closest star system to the sun. And an astronomer at Swarthmore in 1969 published a paper that said, look, I've measured the position on the sky of this star, and the wobble in the plane of the sky is best explained by there being a planetary mass body around this system. And unfortunately, astronomers went back and tried to do the same measurements that Peter Van de Kamp had made, and they did not see what he saw. And it continued to be the case that exoplanets had not delivered the goods, right? There was supposed to be a planet around this system, and it was not rediscovered. And so it was about this time that the number of people working in exoplanets at about this time, people say that the number of people working in this field could have fit in a phone booth. Again, you have to be an older person in the audience to understand what a phone booth was, since they don't really exist anymore. But progress actually was very close at hand. So Dave Latham is an astronomer at the Harvard Smithsonian Center for Astrophysics, and he actually used this Doppler technique, this Doppler wobble, to find what was very, very close to being a planet. It was an object which is 11 times more massive than Jupiter, orbiting its star about the same distance away from its star as Mercury is from the sun in our own solar system. And so this was the first object that we're actually kind of getting close, right? I mean, it's probably too big to be a planet. There's another type of celestial body called a brown dwarf, which is more like a failed star than a planet. And so most people think now that this particular object, HD 114762, is the system, and the planet, or the brown dwarf, would be called HD 114762b, is probably a brown dwarf. But we were finally on the right track here in 1989. And so then it was only 3 years after that that two astronomers used a completely different technique to find a Earth mass object, or two Earth mass objects, around the degenerate core of a stellar explosion. Unfortunately, the planets that they found in this, or the planet mass objects they found in this system, couldn't have formed at the same time the star formed. They would have been lost when the star exploded. So these things were something else. They're interesting, but they're not quite a planetary mass object that formed at the same time the star formed, which is what we think is the situation in our own solar system. And so I belabored this point, but the first successful discovery of a planetary mass object around a star like the sun didn't occur until 1995. This object was called 51 Peg b. The name of the star is 51 Peg. We put a lowercase b next to it to indicate there's a planet around it. And this was exactly what Otto Struve said we should be looking for, but that no one had actually looked for. This was an object which was as massive as Jupiter, so we expected to find it several times the distance away from its host star as Earth is from the sun. And instead, this object was found 20 times closer to its star, where the people who studied at the time how planets should have formed from a physics-based theoretical perspective said that type of planet shouldn't be there. But it was. And this is another recurring theme in exoplanets, that the expectation of what we were going to find in the galaxy based upon our own solar system has led us astray. It's caused us to look for things that may or may not be there, and instead we should be open to the idea that different types of systems can be found wherever we have a new way of looking for them. So I've talked a little bit about this already, but I wanted to get back a little bit more to the technical question of how does one find an exoplanet? So I already mentioned this Doppler technique, and the Doppler technique is very good at finding particular types of planets. Here I plotted the distance from the star in terms of Earth distances on the x-axis, and the planet mass on the y-axis. Here's Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. So this shaded region is where the Doppler technique works best. It finds planets that are more massive than Earth out to distances comparable to the distance to Jupiter. And so right now, we have the ability to find other Jupiters in our own galaxy. Jupiter has an orbital period of 12 years, so this is something that you need 12 years worth of data to find, but now these precise radial velocity surveys have been going on for 20, and in some cases 25 years. So we can find exojupiters, and have found exojupiters. The transit technique, which I talked about briefly also before, can find even smaller planets, at least when you do the transit measurement from space, but because you need this special geometry, you are only sensitive to planets that are much, much closer than Jupiter, perhaps out to the distance of Earth. And even in the case of Earth, even with the best technology we've had to this point, it's really, really tough to find an Earth-sized thing around a star like the Sun, basically because the dip in light is proportional to the ratio of the radii, and so you can only find small things right now around relatively smaller stars. And the telescope which has produced most of the discoveries using this transit technique is the Kepler Space Telescope. So this was a mission, or a telescope, which was launched by NASA in 2008, which stared at this one piece of the summer sky here in the northern hemisphere for 3.5 years. And it stared for 3.5 years because it needed to see a planet that had the same orbital period as Earth, that is 1 year, pass between us and its host star 3 times to be certain that it actually saw a planet and not some other astrophysical system which can produce a similar signal. So the prime mission of Kepler has now ended, and now it's pursuing a slightly different survey where it's looking at multiple pieces of the sky for a slightly shorter period of time, but it's still performing a lot of excellent work. And in fact, Kepler has found the largest number of planetary systems of any telescope that has yet been developed. So there's 2 more things that I wanted to talk about, how we can find exoplanets, and this one is called the microlensing technique. So in this situation, there's a background star, and a star in the foreground, potentially with a planet, passes between us and that star. And it turns out, in Einstein's theory of general relativity, a massive object can act like a lens and effectively focus the light from this background object such that it appears to get brighter from our vantage point. If all there was this star, you would just see this brightening, and then it would fall off. But in this case, there's an anomalous blip. And this anomalous blip is the smoking gun signature of a planetary system around this foreground star. And this microlensing technique is excellent because it's capable of finding super-Earth, that is, things that are several times the mass of the Earth, out to distances beyond the distance of the Earth from the Sun. So no other technique which we have is capable of exploring this or searching for this type of planetary system. And the last technique I wanted to talk about is what's called the direct imaging technique. So this is the simplest possible thing you can imagine. You go out to a big telescope, you point it at the sky, and it actually turns out it's not hard for a modern telescope with modern instrumentation to see the light from a glowing Jupiter mass object. Unfortunately, the Jupiter mass objects are usually right next to a really, really bright star, and the contrast is the problem. But we now have the technology to suppress the light from the host star and just look around its outskirts to look for this type of planetary system. And in fact, this is the most impressive example of a system discovered with direct imaging, which we've found so far. It's called HR 8799. You can see 3 planetary mass objects in this diagram. There are actually 4. A 4th planet was discovered with more advanced data. This was from when it was discovered. But this is a system where there are 4 bodies that are several times the mass of Jupiter, and the system extends out to 70 times the distance between the Earth and the Sun, so more than twice as big as our own solar system. And these direct imaging techniques work best at these relatively large distances from the host star and at relatively high masses. So if I put everything together and show you what type of planetary systems we can find right now, we can find Jupiter. We have a chance at finding Saturn. If we're really, really lucky, we can find Earth. But that's all we can do right now. So what's important to keep in mind as I now talk about some of the exciting discoveries which we've made, that we are completely ignorant as to what's going on down here in the terrestrial planet regime for stars like the Sun. Everything which we know is for planets which are closer to their host star than the Earth or significantly more massive than the Earth. So what are these exoplanetary systems which we've found like? We know of nearly 3,000 such systems. This is an artist's conception where the size of the planets have all been set to the right scale. And so what you can see is we know of lots and lots of planets which are much bigger than the Earth. We know of many, many planets which are also Neptune size. And in fact, we know of very, very few which are like the Earth. So one question you might ask is, what is the closest exoplanet? It turns out the closest exoplanet is called Gliese 15a b. So the star that it orbits is called Gliese 15a. It's in a binary system, so there's an A and there's a B. And the planet which orbits it is indicated with lowercase b. So this planet is about 11 light years away. At the greatest speed which has ever been reached by a human being, which took place during the Apollo 10 mission to the moon, that speed of nearly 25,000 miles per hour, how long do you think it would take to reach this star and this close by planet? 1,000 years? Millions of years. I like the enthusiasm. We're actually doing a really good job because we're bracketing things really well here again. It turns out it would take about 300,000 years to get to this planet going at the fastest speed that's been reached by a human being. And you probably wouldn't even want to go there because this planet is actually so close to its host star that it would be very unpleasant to be on the surface. But we are working on finding closer things, and also I presume some people are working on getting us there faster. But I guess you'd have to have someone from JPL come to tell you about that. So another question you might ask is, what's the smallest exoplanet we know about? So the smallest exoplanet we know about was discovered by this Kepler Space Telescope, and it's in the Kepler 37 system. It's not a very creative name, but it indicates that this was a system which was discovered by Kepler, and in particular, it was the 37th such system. So this is the smallest planet right here, Kepler 37b. So the host star in the system is very close in size to the Sun. But the reason Kepler was able to find such a small planet around it is because the star is very, very bright. If it's very, very bright, it's easy to get precise data on it and find small signals. And then also this planet has a very, very short period. So because it had a short period, there were many, many instances when it passed between the star and our line of sight. So we got many, many examples to try and pull out of the data. It turns out this planet is actually smaller than Mercury and only marginally larger than the Moon. Again, this is not a planet that is habitable. It's not a planet you would want to go to. It's much too hot to exist. But it is interesting that whatever the planet formation process is, it can make something smaller than the smallest planet in our own solar system. Another question you might ask is, what's the biggest exoplanet? Turns out this question doesn't have an easy answer, again, which is going to be another common theme in exoplanetary astronomy and potentially also in some of the questions you might ask after the talk. And the reason is because there's no good boundary between how big a planet could get and how small one of these failed stars, one of these brown dwarfs might get. So to answer the question in terms of mass is actually very, very difficult. It's a little bit easier, though, to answer in radius. Because in this range of mass, as you get to more and more massive things, the object doesn't grow in size. They, in fact, get smaller. And so as you go to more and more massive objects, you get to bigger and bigger radii. And so the answer in terms of what's the biggest planet we know about in terms of its radius is a planet called WASP 79b. So this is a planet which is slightly lower mass than Jupiter. It orbits its star with a period of only 3.6 days. So this thing has 100 years for every year here on the Earth. It's about 20 times closer to its host star than the Earth is to the Sun. And the reason it has such a puffy size is because it's low mass and because it's right next to a really, really bright, really, really hot star there's a lot of energy which is being dumped into its envelope. And so because all this energy is coming in, it gets puffed up. Another question you might ask is, which exoplanet is closest to its host star? In this case, the answer was provided by Kepler again. This one is called Kepler 78b. This object has a mass of about 1.7 times the mass of the Earth. It orbits its star more than 100 times closer than the Earth is from the Sun. And its surface temperature is about 25,000 Kelvin. This is a lava world. If you were hopefully in orbit around it and not on the surface, you would see the part of the planet which is pointed towards the Sun would be an ocean of molten magma. In fact, if you wanted to imagine what hell might be like, you could just imagine what life might be like on Kepler 78b. Another thing you might want to know is which exoplanet is furthest from its host star. Now again, I've mentioned there's this difficulty in saying what is a failed star or a brown dwarf and what is an exoplanet, so I've tried to pick out the most distant thing which we know about that is definitely a planet. And it turns out that object was discovered using the microlensing technique, and this object is called OGLE 2008-BL-092L. That's quite the mouthful, but this thing is a planet which is about 60 times the mass of the Earth, and it orbits its host star at about a distance of 18 times the distance between the Earth and the Sun. So this is actually a Uranus analog system, and so far the only planetary system like this that we know about. Now, I'm about to get to the question which I think most of you are excited to know. What is the most Earth-like exoplanet? It also turns out this is a complicated question. There's lots of different ways for a planet to be Earth-like. Is it Earth-like because it's the same size as the Earth? Is it Earth-like because it's both the same size and has the same composition? Maybe you also need to add plate tectonics for it to be Earth-like. Does it have to orbit a star like the Sun? Can it orbit a more massive star? Can it orbit a smaller star? So depending on how you ask the question, there are many possible different answers. So one thing which I think most people would agree upon is that the planet to be Earth-like, it has to be in the habitable zone. That is, the temperature at the surface of the planet, assuming it's in thermal equilibrium, has to be such that it's not too hot that all of the water hasn't turned to vapor, and not too cold that all of the water hasn't frozen out into ice. It has to be a planet which is just right. Some people refer to this as the Goldilocks zone. And so this is the Earth right here. According to certain definitions of the habitable zone, Mars and our own solar system should be in the habitable zone, and Venus is probably not. So these are listed here, some of the planetary systems which might be in the habitable zone of their stars. It turns out that most of them are around smaller and cooler stars, and so because the star is cool, the planet has to be much closer for it to be warm enough to have liquid water on its surface. And as I showed you before, most of the ways we have to find exoplanets work much better for these smaller stars. If the star is small, the amplitude of the Doppler signal is larger, and the dip in brightness when the star passes between us and its host star is largest, which I've illustrated here on this next slide. So here's the radius of the orbit relative to the Earth's, and the stellar mass of its host star on the y-axis. This is the Sun right here with the solar system. Earth is right smack dab in the middle of the habitable zone. As you go to more and more massive stars, the habitable zone moves further out, and as you go to lower mass stars, it moves further in. This is important because most of the planets that we're going to be able to investigate in terms of whether or not they have indicators of life in the future are going to be around these smaller stars. This is the compilation of small habitable zone planets as of last summer that Kepler had discovered. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 such systems. So while it's great that we know that these systems exist, the fact that they were discovered by Kepler means that because of the nature of the Kepler mission, that they tend to orbit stars which are relatively faint and very far away. Because the star is faint and far away, the amplitude of the signal is small. The amplitude of the signal we need to look for to see if there might be the signs of life on these planets is small relative to the randomness that just comes from the fact there aren't that many photons reaching us from these stars. And so we're going to have to do something else in the future beyond Kepler to actually find these signatures of life on other planetary systems. So this indicates the 20 years of progress. This is an artist's conception of 51 Peg B, which was announced in October of 1995. It was this big Jupiter-sized thing. And this is this Kepler 452b system, this approximately Earth-sized planet around a star approximately the same size as the Sun, quite a bit smaller, and also potentially much more interesting in terms of the implications for life. Another question I'm sure you've probably all thought about is, how many solar systems are there in the galaxy? This is actually something I've thought a little about. And again, it depends on what exactly do you mean by solar system. So do you mean there's a Earth-sized planet in the habitable zone around a star like the Sun? Or do you need other things to be true too? Do you need there to be a Jupiter-sized planet in the system? So we obviously have a Jupiter-sized planet in our own solar system. And some astrobiologists think that's important because a planet like Jupiter can keep the inner solar system, where we live, free from comets. Now, some people have argued that if Jupiter wasn't in our solar system, the Earth would be hit by a massive comet every 100,000 or perhaps every million years. And that would be bad. Right? So maybe you say, well, certainly for intelligent life, you need this planet to be free of cometary impacts. You need to have another Jupiter-sized planet in the system to protect it. So I've actually done that calculation. How many planetary systems are there in our own galaxy where there is an approximately Earth-sized planet around a star like the Sun in the habitable zone, and there's another giant planet like Jupiter outside of its orbit to protect it from comets? Any guesses about what that number might be? 100 million. We have another bid. All stars have solar systems. Okay. So the number which I came out with, and this is, again, certainly this is subject to some uncertainty, is that there are about 4 million such systems in our galaxy. That's comparable to the number of pixels here in this beautiful image of the Griffith Observatory and the city of Los Angeles. Now, if I were to remove the constraint that there had to be a Jupiter-sized planet in the system to protect it from comets, there would be perhaps 20 or 30 million such systems in our own galaxy. So there would be enough such that I could give almost everyone in Los Angeles County a planetary system of their very own. So that's a taste of what we know about right now for exoplanetary systems, but what you and I and most every other one wants to know is, when are we going to be able to find, and in particular, find a planet that might be habitable and that we might be able to search for the signs of life on it? So what does the future hold? So the first thing that the future holds is something called the Transiting Exoplanet Survey Satellite. This is another satellite which is going to be launched by NASA next year, if everything goes according to plan. And this satellite is going to do a very complementary survey to what the Kepler Space Telescope did. Instead of staring at one part of the sky for 3.5 years, it's going to look at the entire sky, but for a shorter period. Instead of looking at relatively faint stars, it's going to look at all of the brightest stars in the sky. And it's going to find planets around these bright stars. And the reason it's important to find planets around bright stars is it's only the bright stars that we can study in sufficient detail to find the signatures of life on those planets. So the satellite is going to observe 1/12 of the sky every month. It's going to do this for the northern hemisphere, or potentially the southern hemisphere. And then it's going to flip upside down and do the other hemisphere that it hasn't already done. And in that way, it's going to find all of the close-in planets around the smallest stars, which we then might be able to observe with the James Webb Space Telescope. This is the successor to the Hubble Space Telescope. NASA plans to launch this telescope in 2018, if everything goes according to plan. And this is going to be exciting because the combination of the discoveries from TESS And the new observational capabilities of the James Webb Space Telescope are going to allow us to look for these things in the atmosphere of an exoplanet. In particular, I'm talking about molecular oxygen, ozone, water vapor, more water vapor, some carbon dioxide, and methane. And so if we look at one of the transiting planets which has been discovered by TESS, and in particular if it is a small star and a slightly bigger than Earth-sized planet, and the star that it's orbiting is very bright, what you can do is you can take an infrared spectrum of that host star during the transit of the planet. And then what you do is look to see if the planet appears to be bigger where there should be oxygen or carbon dioxide or methane in its atmosphere, right? The planet will appear bigger because it has these things in its atmosphere. These molecules in its atmosphere are absorbing the light at those wavelengths and letting it pass by at other wavelengths. And so the signal that you look for is a planet which looks big here where there's a lot of methane, or looks big here where there's a lot of ozone, and looks very small here when there's very little of anything else. That's how we're going to look for oxygen and ozone and methane and some other molecules which are not indicated here, methyl chloride or nitrous oxide, which might be more important for the atmospheres of these small planets around small stars. But the James Webb Space Telescope is an extremely valuable piece of equipment. All the astronomers in the world are going to want to use it. And to actually detect these signals, you would have to observe one of these transits many, many times. And so you're only going to be able to do one or perhaps a handful of such systems. You have to have some other way to do the majority of the objects you're going to find, either ones which are just a little bit fainter or ones that, for whatever reason, were not favorable for the space-based telescope. And what's going to happen is that in the next 10 years, we're going to have the next generation of ground-based optical and infrared telescopes. Here I've shown a cartoon or an image of the Giant Magellan Telescope, which astronomers at the Carnegie Observatories and other institutions across the United States and at some international partners are working on. And this telescope is going to be in Chile. And instead of having a diameter of 6 or 10 meters, which is how big the biggest telescopes available to astronomers that are going to have, it's going to have a diameter of nearly 30 meters. And it turns out that in this case, the important scaling is with the size of the primary mirror squared. So this telescope is going to be an order of magnitude more powerful than the most powerful telescopes we have on the Earth right now. And it's going to be able to do many of the same things that the James Webb Space Telescope could do, except because it's so big, it's going to be able to do it for even fainter objects, which means it's going to be able to do it for a much larger sample than what the space-based telescope is going to be able to do it for. So that's going to, not only that, it's going to actually be able to be used to measure the masses of these objects, right? Because if you use the transit technique, all you get is the radius. You actually need to use the Doppler technique to measure its minimum mass, and in this case, its mass. And so the Giant Magellan Telescope and the other 30-meter class telescopes that are being built are going to be the instruments that are going to weigh these Earth-sized planets. And then finally, the next telescope which is coming in this parade of NASA telescopes is something called the Wide Field Infrared Survey Telescope. And what it's going to do is twofold. First of all, it's going to use this microlensing technique to stare at the dense stellar field towards the center of our galaxy. And it's going to find thousands of Earth and super-Earth-sized planets that are, say, 5 times further away from their host star than the Earth is from the sun. So it's going to explore a completely unexplored parameter space and tell us an enormous amount about how planets form. Not only that, there's a lot of talk right now about building a subcomponent of this telescope to block out the light from stars like the sun, such that this telescope would actually be able to collect photons from Earth-sized planets in the habitable zone of stars like the sun. And if you can collect photons from it, you can actually start to build up the spectrum, or how does that planet look? And so this is going to be the thing which, should we find a Earth-sized planet in the habitable zone around a star like the sun nearby to us, This is going to be the telescope which is going to take the picture of it and tell us whether it's blue or green or something else. Great, that's all I wanted to say. I'll take questions. Okay. You there?
You're mentioning all the telescopes made me think about this. I've never really thought about this before. There is a lot of space junk, and there are asteroids zooming around and all that. They crash with the Earth, even though there haven't been incidents. Has an asteroid ever collided with a satellite, and what would happen?
So the question is, has an asteroid ever collided with a satellite, and what would happen? So it's certainly the case that very, very small pieces of rock or other space junk can collide with satellites in orbit of the Earth. And what usually happens is very, very bad for the satellite. Usually the satellite ends up being damaged and potentially destroyed. So this is something which people actually worry an enormous amount about, is first of all, doing everything that they can to minimize the amount of these little bits of debris, or most of the things which are up there are debris, they're not asteroids. So minimize the amount of debris possible. And then people are also exploring ways to kind of deorbit this debris once we know what it is, using lasers and other more fancy ideas. But it's true that these things, a satellite getting hit by an asteroid or a piece of space junk is very, very bad. And so usually catastrophic for the satellite itself.
There's an emerging theory that Planet X or Planet 9, that it's a planet in our solar system that has a large inclination, the solar system. Has any of these exoplanets been hit that scenario of a perpendicular?
Yeah. So the question is, do we know of any exoplanets that are similar to this proposed Planet 9? So Planet 9 is a planet which is perhaps 10 times, or a proposed planet which is about 10 times the mass of the Earth, orbiting the Sun at about 300 times the distance the Earth is from the Sun. And also, it is oriented such that the 8 planets that we're certain about in our solar system are all in a nice orderly disk, whereas Planet 9 is inclined at an angle of something like 40 degrees. So very, very strange given how we think our own planetary system and planetary systems in general might have formed. But it does turn out that there are now many examples of planetary systems where the star rotates like this, and the planet, goes around even like that, or is even retrograde, which initially were unexplained in our models of planet formation. So there are lots of physical ideas about how those systems might have been formed, and that's a very active area of research. But none of the scenarios which have been proposed in that situation are specifically applicable to Planet 9, although more general scenarios of that same type might be used to explain Planet 9.
Have you ever discovered or seen that maybe more than one exoplanet orbiting the same star? Would that be hard to break apart the information?
No, so it is actually now quite common that we see planetary systems where there are several planets orbiting the same star. So Kepler has discovered, I think, about 1,500 of this type of system. We know of perhaps 30 or 40, perhaps even 50 from that radial velocity technique. So it certainly seems to be the case that if you see one planet in a system, there are very likely to be more. And so it is indeed true that this makes the data harder to analyze. So in the radial velocity technique, instead of having one nice sinusoidal oscillation, you have multiple sinusoidal type things at different periods. In fact, does make the analysis much harder. For transits, it also makes the analysis harder, but if you have good data from Kepler, then Kepler makes it easy because Kepler data is amazing.
I read online today that some astronomers announced the discovery of 3 exoplanets in a habitable zone orbiting a dwarf sun, like 39 light-years out. I was wondering, the article seemed to indicate that there was some newness to the fact that they found planets orbiting a dwarf sun. If you're aware of that, I was wondering if you could comment on that.
Yeah, so the question was about a planetary system that was just announced today called TRAPPIST-1. So TRAPPIST-1 is a system of 3 planets, all more massive than the Earth, which orbit a star which is perhaps 1/12 the mass of the Sun. And this is exciting because we've never seen a planetary system around this type of star before. And in particular, the lowest mass stars are also the most frequently occurring stars in the galaxy. And so this might be the first example of the typical planetary system in the sense that it's the type of planetary system known around the most common type of star. So there are 3 planets in the system. The closest 2 are inside the habitable zone. They're much too hot. But the most distant planet, which is also the biggest and perhaps least Earth-like, might actually be in the habitable zone. So this planetary system is, 39 light years away is not especially close, especially for the star is so low mass, it's also very dim. It turns out that the brightness of a star, at least how bright intrinsically a star is proportional to how massive it is. And so because this star is so faint, it could be, it's certainly not impossible, but it will be more difficult to measure the properties of these planets than it would be if the star was somewhat brighter. So for example, the only data we have about this system comes from observing them with the transit technique. The host star right now is too faint to observe with the Doppler technique, and so we don't know how massive the planets are. We know how big they are, but we don't know how massive they are. And so we don't know their density, we don't know what they're made of. And so this is obviously a very exciting discovery, but it's going to take a lot more work to fully exploit it. In the back? Okay, that's an excellent question. The question was, how will the new capabilities which are coming online affect or allow us to discover new systems? So the TESS is actually not going to really push, so TESS uses the transit technique. It's not going to push this curve down so much as it's going to find lots of this type of system which Kepler already found, but find examples which are much easier to study. So most of the things which Kepler found orbit very faint stars. We can't use the Doppler technique on them because the star is too faint. So all we know is the size. We don't know the mass of the planet. And if we knew the mass and the size, we could measure its density, for example. It is going to, though, find the smallest planets which one could do ground-based follow-up for. So TESS is going to be exciting, not that it's going to discover the smallest things, but it's going to discover the small things which we can study more. JWST is going to, and the 30-meter class telescopes is going to allow us to study both the atmospheres of the things which TESS finds, but then also, at least in the 30-meter telescope case, allow us to measure their masses again. You need both the radius and the mass to get the density to say what is this thing actually made of. And then WFIRST, using the microlensing technique, it's actually going to allow us to find things that are maybe all the way down to Mars size. So it's going to be down all the way like that. The problem, again, though, with WFIRST is the planetary systems it's going to find are going to be around stars which are so faint it's going to be difficult to study them in detail. So it's good to know that they're there. You can calculate how frequent they are, maybe what their mass distribution is, but we're not going to learn much beyond that, at least at first. Over there? Yeah. Uh-huh.
There seems to be a jump.
Yeah, so the question was, I'm guessing, what was the cause of the jump in the number of planets known with time? And the cause of the jump was the prolific Kepler Space Telescope. There was a big announcement of many new systems, which was made, I guess that would be in 2014. Yeah, so it was a major announcement of new planetary candidates from Kepler. So it was so Kepler it gained sensitivity as a function of time, both because it explored more distant planetary systems and because you got more data for the closest in ones. And so it was able to find smaller and smaller and more distant things as time went by. So it turns out that small things are more common, distant things are more common, and as you say, the data processing improved. So all those things together allowed this big discovery to happen relatively late in the mission. You?
When you say habitable zone, do you mean fit for human habitation or that like as we know it on Earth?
Yeah, so the question was, what do I actually mean by the habitable zone? And so the habitable zone, at least in the context which I was describing it, is very, very simple. All it means is that the planet is cool enough that the water should not be in vapor form, and warm enough that it should not all be in ice. That's all I mean, is that one might expect there to be liquid water on the surface if the atmosphere is comparable to the atmosphere of the Earth. There's many, many more things which go into it than that. For example, what is the atmosphere actually made of? Is there or is there not plate tectonics on the planet? Like I indicated before, Venus and Earth in many ways are exactly the same planet. Venus is incredibly inhospitable to life like us, and Earth is very hospitable to it. And we have, as exoplanetary astronomers, we don't have any good idea about, right now, what particular Earth-sized planet is going to be habitable, because we don't even understand it in our own solar system right now.
Then another question that follows that is that, are you looking for other forms of life that may not exist in what defines the habitable zone?
Yeah, so the question is, can we look for other forms of life beyond life like us? And so the program basically is find all of the systems which one can study in this way, study all of them, and then sort it out once we've collected the data. We don't know what we're going to find until we look. In the middle, right there.
So the Milky Way has what, maybe 300 billion stars or so. What percentage of those would you guess have planets?
Yeah, so at least for stars like the Sun, it turns out about 10% of the stars in the Milky Way are stars like the Sun. As far as we can tell, at least theoretically, terrestrial planetary systems are ubiquitous in the sense that no matter what you do, you make something which looks like a terrestrial planet system. We do know that bigger planets like Jupiter and Saturn depend on the composition of the star. So in particular, we know that big planets like Jupiter and Saturn are preferentially found around stars which have lots of rock-making elements like magnesium and calcium and titanium and things like that. So that the probability that a star in the galaxy has a Jupiter-sized planet is a function of its composition, whereas as far as we can tell, relatively small planets don't care about that. And so I would say, at least for the Sun, if I had to guess, I would say that most stars in the galaxy, like the Sun, have a system of terrestrial planets. But right now, that's beyond our capability to measure. And even in the future, our capability to measure them depends on their orientation of its planetary system relative to us. And so even if every star has one, it doesn't mean we're going to detect one around every star, given our own technology. But I would guess that planetary systems like our own terrestrial planets are common. Planets like Jupiter are found around a few percent to perhaps 10% of stars like the Sun. We don't know what the planetary systems around stars more massive than the Sun should be like, and we're only just now learning about what planetary systems around stars that are smaller than the Sun should look like. Again, this is this TRAPPIST-1 discovery, which was just announced today. So it depends on what type of star you're talking about. But I would say there should be a very large number of terrestrial planetary systems, again, perhaps up to 100 million in our own galaxy. You in the green shirt? Yeah. I'm sorry. I'll be sure to get your question next. Yeah.
Given the distances that we're looking at to find this, even if we find a perfect planet in the perfect zone, and it has water, and it has an atmosphere, it has tectonic plates, are we just trying to find one in the hopes that somehow we're going to come up with some other technology to actually get there?
Well, I mean, so it would be interesting to find one, but ultimately what we'd like to do, so what I'm most interested in, so I am interested in understanding life and the consequences of that, and what other types of life and the existence of life in the galaxy. I'm interested in knowing how is it that planetary systems like the Earth might have formed? What other properties of the system, either based on the star or in its past history, might have led there to be a planet like Earth there and not in some other system. It might very well turn out to be it's random. There's no way to predict based on even knowing perfectly what the initial conditions are, whether or not a planet like Earth would form. But we have to have more data to start unraveling it. It's just completely hopeless to do just using physics and trying to do a first principles type calculation. So independent of whether or not we can do anything about the life or interact with the life or whatever, it's interesting to astronomers and exobiologists to understand how the system like that could have even formed. Okay, so the red shirt?
Considering you have to use adaptive optics for the land-based telescopes, and there's a reduced depth of field because of the adaptive optics, is that causing you a problem when you're trying to use these experiments? Because in order to see with adaptive optics, you lose your depth of field. Is that affecting your ability to look at it?
Yeah, so the question has to do with adaptive optics, which is a particular technique which is used on state-of-the-art telescopes right now to cancel out the effects of the atmosphere and make the telescope behave as if it was actually in space. And there are historically been limitations to these techniques that require a very bright star to be very close to the star you're studying, because you need to observe the bright star to determine what you need to do with the adaptive optics system to make it work. There are now certain adaptive optic systems that have a laser beam which excites the sodium layer high in the Earth's atmosphere to create an artificial star, which you can then use to do this correction. And that's not ideal, but it does work for the most part. And it's also the case that the reason the adaptive optics fields of view have been so small, it's because you need a very special electrical component called an actuator to kind of deform a mirror that you can deform to arbitrary shape. And historically, it's been very difficult and very expensive to build a very large mirror like this. But the technology is advanced to the point we actually can start to use significantly sized deformable mirrors, and in particular, use them in different places in the optical system and a telescope, which make them very effective. And so there has been a lot of work recently which has kind of helped mitigate that. We are working on using adaptive optics over much larger fields of view. But certainly it helps for the radial velocity technique to use adaptive optics, but because you're just taking a high-resolution spectrum, you win just by having the big light bucket. You don't need the adaptive optics to do the radial velocity measurements, which will allow you to measure the masses of these small planets. So that is independent of the adaptive optics.
In other exoplanetary systems, are you able to tell if all the planets are rotating in the same plane like our solar system, or if the planes of the planets are randomly along?
Yeah, so in the systems of multiple planets, which Kepler has seen, we actually know that they have to be reasonably close to alignment. If they weren't all close to the same plane, then we wouldn't see all of them transit. Just the fact we see multiple transits means we know that they are in the same plane. There is, for the radial velocity technique in general, you can't do that. There are a handful of giant planet systems that have been discovered with the radial velocity technique that, because they're in a multiple planet system, and the multiple planet system has special characteristics, that you can use a theoretical model for how a planetary system might evolve using Newton's theory of gravity to say that because the planetary system is billions of years old, it's lived long enough for us to come along and observe it. That means that it almost certainly has to be dynamically stable. There are constraints that stability can give you, which can tell you that certain ones, and in particular the one I'm thinking about is I think called GJ876, that this planetary system, which has multiple giant planets, has to be well aligned. But in general, it is very difficult to tell what the mutual inclination is. But at least from Kepler, we know that well-aligned systems of at least small planets seems to be the main mode of planet formation. That is, what we would expect based on our own solar system does seem to be the case, at least for small planets. There?
Several times you have linked plate tectonics to the habitable plot.
So at the most basic level, this has to do something called the carbon cycle. So if you have plate tectonics, you have this constant recycling of carbon. So it helps provide a feedback loop. So imagine that more carbon dioxide starts to enter the atmosphere. It turns out that more carbon dioxide in the atmosphere typically leads to more weathering. And so if you have more weathering, you have more weather, you have more erosion, and you have more stuff either running off and ending up in the ocean, or more stuff being exposed. And more stuff being exposed basically provides the feedback loop to this thing. So if you have more carbon, you have more weathering, you expose more rock, and that ultimately helps, combined with plate tectonics, take carbon dioxide out of the atmosphere. And then if things start to get too cold, you have less weathering and you have less of this feedback cycle, and then you have more volcanism, which introduces carbon into the atmosphere, which then builds up until it gets warm again and you have more weathering and you have more carbon being taken out. So ultimately, plate tectonics is important in the carbon cycle, which helps regulate climate on a planet like Earth.